Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're doing a deep dive into Unit 12, Atoms. We'll be focusing specifically on alpha particle scattering and, the Rutherford nuclear model that came from it. We'll keep it simple, exam-safe, and really clear up why this one experiment changed physics forever. Okay, so to start, let's think about something you see almost every day. Have you ever really looked at a neon sign? It always glows that specific red color. Or a sodium street lamp, which is always that distinct yellow.
That's true.
Why are those colors so absolute? Why don't they just glow white like a normal bulb?
That is a great question. I mean, we just take it for granted, but you're right. Why is it that neon is only red and sodium is only that particular shade of yellow? There must be a reason.
Exactly. And here's the counterintuitive part. You might think only really hot things glow, right? Like a bulb filament. But a neon sign, a gas discharge tube, is often quite cool to the touch. Yet it produces this vivid, specific color. So this tells us the color isn't just about temperature. It's coming from something deep inside the material's internal structure. And understanding that structure, well, it all started with a huge surprise. An experiment that gave an answer nobody expected. The Rutherford scattering experiment.
So this experiment was the first real peek inside the atom.
It was the experiment that kicked the door down. See, before 1909, the accepted model was J.J. Thomson's plum pudding model. It basically suggested the atom was a uniform ball of positive charge.
Like a watermelon.
A watermelon's a great way to think of it, yes. A soft sphere of positive charge, and inside it you have these tiny negative electrons embedded, like the seeds. So Rutherford decided to test this. He took these fast, heavy alpha particles, which are basically helium nuclei, positively charged, and he fired them at a very, very thin sheet of gold foil.
Okay, so if the atom really was like this soft plum pudding, what should have happened to those alpha particles when they hit the foil?
Logically, the prediction was very clear. If the positive charge is spread out thinly, like in a pudding, its electric field would be very weak. So the heavy, fast-moving alpha particles should have just passed right through.
With no deflection at all?
Well, maybe a tiny bit. A minor, gradual, small-angle deflection. A slight wiggle in their path as they pass through that weak, positive pudding. But large deflections, bouncing straight back. That should have been completely impossible. Let's use an analogy to make this really solid. Imagine you're throwing tennis balls, those are your alpha particles, into a massive empty cricket stadium. The stadium is the atom.
Okay, I'm with you.
If the stadium were filled uniformly with soft cushions, that's the plum pudding model, your tennis balls would just push through, maybe slow down a bit, but they would never ever bounce back at you, right?
No, of course not. They'd just sort of push the cushions aside and keep going.
Exactly. But now, what if the stadium was almost completely empty, except for one single, tiny, incredibly hard marble placed right on the center spot?
Then most of the tennis balls would miss it and go straight through.
Yes. Most would pass right through the empty space.
Yeah.
But the very, very few that happened to hit that tiny hard marble dead on.
They would bounce back violently.
And that is exactly what Rutherford's team saw. They were stunned. Most of the alpha particles, over 99%, went straight through as if nothing was there. But, and this is the critical part, about 1 in 8,000 of them were deflected by more than 90 degrees. Some even bounced straight back.
1 in 8,000. That's such a tiny number, but the fact that it happened at all means the plum pudding idea must be completely wrong.
Completely and utterly wrong. Rutherford famously said it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
Yeah.
It forced this massive realization. The atom has to be mostly empty space. All the positive charge and almost all the mass must be concentrated in a tiny, dense core, the nucleus.
So that single hard marble in the stadium, that's the nucleus.
That's the nucleus. Now let's look at the formal setup of the experiment as you'll need it for your exams. It's often called the Geiger-Marsden experiment.
Right, after his students who actually did the counting.
Correct. So they used a radioactive source, specifically bismuth-214, to get the alpha particles. Then they used lead bricks with a small hole to create a narrow collimated beam. This beam was aimed at an extremely thin gold foil, only about 2.1 times 10 to the power of -7 meters thick.
How do they even see where the particles went? You can't see alpha particles.
Good question. They had a movable screen made of zinc sulfide that surrounded the foil. Whenever an alpha particle hit this screen, it would produce a tiny flash of light, a scintillation. And they sat there, in the dark, with a microscope, counting these flashes, angle by angle.
Wow, that must have been incredibly tedious work.
It was. Now, could you please read the formal description of the setup from the answered material for us?
Of course, it says, alpha particles emitted from a text by a radioactive source were collimated into a narrow beam by passage through lead bricks. The beam fell on a thin gold foil, thickness 2.1 by $10 nullars. Scattered alpha particles were observed via scintillations on a zinc sulfide screen viewed through a microscope.
Perfect, thank you. Now let's nail down the 3 key conclusions from these observations. This is the heart of the matter. First observation. Most alpha particles pass straight through or with very small deflections, less than 1 degree. The conclusion from this is simple and profound. The atom is mostly empty space.
Okay, that's clear. The particles pass through because there was nothing there to hit.
Exactly. Second observation. A very small fraction, about 0.14%, scattered by more than 1 degree, and that crucial 1 in 8,000 deflected by more than 90 degrees.
Ones that bounced back.
Yes. The conclusion here is that to cause such a massive repulsion, the entire positive charge and almost all the atom's mass must be concentrated in a volume that is thousands of times smaller than the atom itself. We're talking an atom size of about 10 to the minus 10 meters, but a nucleus size of maybe 10 to the minus 15.
That's 100,000 times smaller. That's an incredible difference in scale.
It's phenomenal. Third point, the mechanism. What force caused this? It was purely the intense electrostatic force of repulsion, Coulomb's law, between the positive alpha particle, which has a charge of plus 2e, and the positive nucleus with charge plus z.
I have a doubt here. What about the electrons? They are also in the atom. Why don't they deflect the alpha particle?
That is a very sharp question and a common point of confusion. The reason is mass. An alpha particle is nearly 8,000 times more massive than an electron, and it's moving at high speed. An electron trying to deflect an alpha particle is, well, it's like a mosquito trying to stop a speeding truck.
So the electrons are just too light to have any significant effect.
They are completely negligible in this interaction. Only the massive, concentrated positive nucleus has the power to cause that large angle scattering. Hope everything's clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's quickly discuss a related calculation, the distance of closest approach. This is what gives us an actual estimate for the size of the nucleus. Think about the most extreme case, a head-on collision. The alpha particle is aimed directly at the nucleus. As it gets closer, the Coulomb repulsion gets stronger and stronger, slowing it down.
Okay, so it slows down, and then
At some point, it will momentarily stop, just for an instant, before being repelled straight back. The scattering angle is 180 degrees. At that exact point, its journey's end, all of its initial kinetic energy has been converted into electric potential energy.
Conservation of energy. So the initial kinetic energy, K, equals the final potential energy, U.
Precisely. So we can write K equals U, and the formula for U is, well, it's the standard electrostatic potential energy formula. From that, we can solve for the distance, d. For a 7.7 MeV alpha particle hitting a gold nucleus, this distance of closest approach comes out to be about 30 femtometers, or 3 into 10 to the minus 14 meters. This gives us an upper limit on the size of the nucleus.
And that confirmed that the nucleus had to be incredibly tiny.
It did, but, and this is a huge but, Rutherford's success created a massive new problem. His model, the planetary model, with electrons orbiting the nucleus like planets, it was unstable, according to classical physics.
Unstable? Why? The planets orbit the sun just fine.
Because the forces are different. Planets are ruled by gravity. Electrons are charged particles ruled by electromagnetism. And classical theory was very clear. Any accelerating charged particle must radiate energy.
An electron in an orbit is constantly changing direction, so it must be accelerating.
Constantly accelerating. So it should be constantly radiating energy, losing speed, and spiraling.
Spiraling into the nucleus. The atom should collapse.
Instantly. In about 10 to the power of minus 8 seconds. But atoms are stable, aren't they? And this model also couldn't explain those specific colors, the line spectra we started with. This failure was critical. It showed that the classical rules don't work inside the atom, and that paved the way for Niels Bohr's quantum revolution. Now, let's tackle 2 silent killers, common misconceptions that can cost you marks in the exam.
Okay, I'm ready. What's the first one?
The first wrong idea is that the atom is a solid object, like a tiny marble. Students see a solid gold foil, and they think the atoms inside must also be solid.
But we just established that's not true.
It's not. The correct idea, Rutherford's great discovery, is that the atom is almost entirely empty space. The nucleus occupies about 1/1,000,000th of the volume. The rest is just nothing.
So I have to remember, atoms are mostly empty, like a huge stadium with just a single marble in the middle.
Perfect. Here's a hook. Atoms are mostly nothing. The nucleus is everything.
Okay, got it. What's the second trap?
The second wrong idea is that the alpha particle gets scattered by hitting the electron cloud. Students think, well, the electrons fill up that empty space, so they must be doing the scattering.
I actually asked about that. It's the mass difference, right?
Exactly. It's a huge mass difference. Electrons are just too light. It's not a mechanical collision like two billiard balls. It's an electrostatic repulsion. And only the massive, concentrated positive charge of the nucleus is strong enough to cause that large angle backscattering.
Right. So the key is that only the heavy nucleus is responsible for the large angle scattering, not the light electrons.
Perfectly stated. And the hook to remember is, electrons are too light to scatter alphas. Nuclei do the scattering.
Yeah.
All right, to help you remember all this, let's use a few memory anchors. First, a catchy phrase for the whole experiment. Most pass through, some bounce back. Rutherford's scattering reveals the nucleus.
I like that. It's simple and covers the main point.
Now, a physical gesture. Imagine you were throwing balls. For most of them, your hand just passes through empty air. Whoosh, straight through. But then, for one throw, imagine your hand suddenly hits an invisible hard wall and bounces back violently. That shock, that bounce, is the 1 in 8,000 event.
That physical action really helps to visualize the surprise of it.
And finally, a fun association. Think of that 1 in 8,000 backscattering event as a lottery ticket. An incredibly rare, shocking surprise that won the grand prize of revealing the secret heart of the atom. Okay, let's wrap this up with a 3-point exam-safe summary. First, Rutherford's experiment proved that the atom is not a uniform pudding. It consists of a tiny, dense, positively charged nucleus, which contains most of the mass, surrounded by vast empty space where electrons are. Second, the key observation was the rare large-angle backscattering. This directly contradicted the plum pudding model and is caused by the strong Coulomb repulsion between the positive alpha particle and the concentrated positive nucleus. And third, while his nuclear model was a huge success in defining structure, it failed classically. It predicted that orbiting electrons should radiate energy and spiral into the nucleus, making atoms unstable. This failure was crucial as it necessitated the development of Bohr's quantum postulates. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive.
See you in the next deep dive.